Okay. Good morning. I know it's too early. I've just made this video at 6:37. Because I might be a little bit busy during the day, so I just decided to have it done now so that I find time to upload it on YouTube. My name's Mulenga Kunda, and my line is +260975578 694. That's the number that you can reach me on WhatsApp, call, text, as well as any other form of communication. Forget about the name of the place here. Just forget about it. Let me even hide it. Okay, forget about it. Okay, so those are my details. On my YouTube channel, you can just search for that name that's right over here, and then you get to have even this video found on YouTube. You just search for that name, and you can reach me on WhatsApp, calls, text on that number. So today I want us to look at the basics of chemistry. Basics of chemistry, in that the periodic table is one of the basic components that are there in our 51 24 stroke 2 subject. This is 515124. This is a science code, and then paper 2, that is chemistry. Now, unfortunately, this is a second component of the periodic table. You can look up for the first component so that you can connect. However, without wasting much of the time, let us look at what we have here. So what we have here is that we have the periodic table that we're gonna look at. Okay, now the previous video has got a lot of things explained. This part is just the continuation of what was earlier discussed. So we are going to start looking at the group 7 of the periodic table. The previous video, that the other video that I'd made was talking about other groups such as group 1, group 2, group 4, and all other groups. But this one is just talking about the group 7. Now, before I rush taking in consideration other people might have just seen this video without seeing the previous one, let's talk about the group 7. Which ones are they? You see these numbers here? These numbers here are representing the group number. These numbers are representing the group number. Yeah, and then these numbers here on your top left, on your left rather, these ones are representing the periods that are determined by the number of shells that are occupied by the electrons. Okay, then these ones here are represented by the number of electrons in the last shell. Even as you get to have the number of shells determining the period, then we'll go to the last shell. Yeah, you go to the last shell and consider the number of electrons that are there in, then you get to have these groups determined. So now we are looking at the group 7. Which ones are the group 7? The group 7s are these ones here. These ones here. So these are the ones that we'll be talking about. Now, do not be deceived by these ones that are here. these elements that are here, do not be deceived by them, whereby you start extending, the group goes all the way up to the hidden here and the NO. No, forget about this part here. We're just interested in these ones here. So when you, even as we get to look at the group 7 elements, these are the ones that we're going to be talking about. So that means we'll be talking about fluorine, you talk about chlorine, you talk about bromine, you talk about these, by the way, these are diatomic elements. I'm just writing the way they are on the periodic table. Then you talk about the iodine, then you also talk about astatine, AS. It sounds English, astatine, or 18 rather. Astatine. So these are the elements that we'll be looking at. But the previous presentation that I've had talked highly about these elements, their name, their physical and chemical properties. So we won't go back to that. We'll just look at the work that is there for today. So what do you have there for today? We have their side effects. That's what we'll start with. So when you say the side effects of these elements, what are we talking about? We're talking about the things, the dangers of having them in the environment. Yeah, and from a physics point of view, we've heard of what we call electromagnetic spectrum. I believe so. Electromagnetic spectrum. I believe you've heard of it. This is a band of components that are present in the light. Now you see, from the sun we have 7 components, and those 7 components are the ones that are combined, and we call them the electromagnetic spectrum, where we've got the UV, which is the ultraviolet, we have the IR, infrared, we have the visible light, we have X-ray, we have Y-ray, we have TV wave, we've got radio wave, we have got microwave. As you advance in your studies, we even find cosmic ray. Yeah, these are the ones that I'm talking about. So now the band of these, they make up what we call the band of these. That's what makes up the electromagnetic spectrum. Now within the electromagnetic spectrum that we have here, you see, we have this guy here. This guy here doesn't seem to be friendly. Where is he? This guy here, the IR. The infrared. The infrared is a component that is there in the electromagnetic spectrum that gives us the pinch of the skin. You go outside. When you go outside, and then you find you find it is very, very hot. You feel the pinch of the skin. That pinch of the skin is because of the presence of this infrared in the beam of light. So now, why am I saying this? I'm trying to just lay the foundation so that even when we get to talk about these things, you know where we're going, okay? So what does that mean? What it means is that if this is the Earth, and then we have a sun here, when these rays are coming, we have a shield that slightly protects us from the dangers of the IR. Okay, these vicious rays, the IR, we have a shield that protects us slightly, and that shield here is a layer which is located way high in the atmosphere. This is what we call ozone. This is what we call ozone. Now, the way these rays, these vicious rays, come approaching us, they are not that friendly. So what happens is that we have this shield that makes sure that we are slightly protected. Okay. Now, in the presence of these group 7 elements, the layer of this ozone layer starts depreciating. Now, when you say depreciation of the ozone layer, what we're talking about is that this layer, which used to be thick, is now becoming very thin. Why? It is because of the reaction of the ozone layer with these group 7 elements. How that happens, I may not explain because the science doesn't talk more about that. Okay, doesn't talk more about that. But all in all, the only thing that I can ask you to remember is that the ozone layer is depreciated by the action of the group 7 elements. Okay. Now, these group 7 elements. That's now. Before I even got that, that reminds me of the negligence that we have, okay, especially in Africa, where someone will just get to have the fridge stops working, and then gets it and goes and dumps it anywhere. Okay, the fridge is, we're going to talk more about this when we go to organic chemistry. I just want to bring and borrow this from the future, CFC. Okay, I don't know if I've heard of CFC. CFC CFC stands for chloro and then fluorocarbon. Okay, CFC stands for chlorofluorocarbon. These things come from the dead fridges, and then we're going to understand better how the ozone layer is depreciated by the actions of these guys, the chlorine, the fluorine, which are examples of the group 7 elements. Okay, so I think that's the only thing we can say about the group 7 elements, because that's the last part anyway. Now let's go to the presentation for today, which we'll have to start looking at the group O elements. Okay, the group O elements, what are they, and what do we know about them? Now, if you can allow me to go back slightly and look at this periodic table right over here, and then we'll have to look at this number here, okay, on your top right. But there's something fish about this. I don't know if you are seeing this. Look here, group 1. Here, group 2, we jump this D block, we go to group 3, group 4, group 5, 6, 7. Now, instead of having group 8, we go back to group O. Isn't that strange, friends? So let us see how that is possible. Let us see how that is possible. Now, we expected to have an 8 here, but the truth of the matter is that there is a 0. And why a 0? These are the things that we are going to look at. I just wanted you to understand that. So let us go back to the part where we were. Let us go back to the part where we were. So when you say group O elements, let us know what they are. Before we go to look at the name, let us first understand these guys. So the first one is helium. Helium, which is He, and then we have a 4 here, and we have a 2 down here. I may not go through them all. So this is helium. Now look at the number of electrons. There are 2, so you can only have 2. The first shell. Okay, the first shell and is the first and last shell has 2 electrons. The other one is neon. Neon is Ne, We have Ne20, if my memory serves me right, then here 10. So if you are to do the configuration of these electrons, you will find that these 10 electrons will be written 2, 8. Okay, this guy has 8 electrons in the last shell. Wow, let's go to argon. Argon, AR right here. I'm not too sure about the mass number, but I'm just interested in the atomic number. But these guys have got magic number. I think it's supposed to be 32, if I'm not mistaken. So if you do the configuration of these 18 electrons, you have 2, then you have 8, you also have 8. Now, what can we say about that? This guy also has 8 electrons in the atom shell, and this guy's got 8 electrons in the atom shell. After the 8 electrons, the next one does not have anything, we'll put a 0. After this one, the next one doesn't have anything, we'll put a 0. And after these 2 for helium, the next one doesn't have anything, we'll put a 0. Now let's go back to the debate. The debate of saying this guy is supposed to be in group 8, this guy Neon agrees to the fact that we can say group 8 because there are 8 electrons in the outermost shell. Argon also agrees to that because it has got 8 electrons in the outermost shell. So if we were to say they are in group 8, then we could, but we're gonna disadvantage the helium because the helium does not have those 8 electrons, yet it only has 2. So because of that, we're gonna say after the last shell is fully occupied, after the shell is after the fully occupied shell, yeah, after the fully occupied shell, how many electrons are in the next one? You can see that this guy's got 0, this guy's got 0, and that guy's got 0. Therefore, they agree to say we're gonna call them group 0. Why? Because after the fully filled shell, the next one does not have anything. Therefore, it's in group 0. Okay, I was just trying to introduce to you why these guys are called group 0 instead of group 8. So from that, then we can now go to the other elements. We've got krypton, Kara, we've got xenon, Ze, and then we've got radon, Rn. Eastern people from Eastern will read this at random. Guys are no, yeah, but it's not random, guys. It's radon, Rn. Okay, so now what are they called by? They are called by any of these names: noble gases, inert gases, and rare gases. But there's a word of great interest: inert. Something inert. If you say I'm trying to providing an inert atmosphere, meaning you're providing an atmosphere where no chemical reaction should take place. Okay. So having known the actual element that are in group O, and why are we saying inert? Now, if you look at the previous presentation that I've had, okay, let me just bring them back. Okay, just bring them back. Okay, let me just bring them back. Okay, very good. So see here, the helium has got 2 electrons fully occupied. This guy's got 8 fully occupied. This guy's got 8 fully occupied. That means these guys, they do not have any loose electrons that can be used for bonding. So because the shells are fully occupied, all the shells that have electrons are fully occupied, therefore they are very much unreactive. So their unreactivity is what brings about the name inert gases. So they are inert gases because they are very, very much unreactive. So that point has been even proven here. Try to use a different color. So we're saying that these guys are called inert gases because they are very, very much unreactive. They are chemically unreactive. And their chemical unreactivity is explained in this point right over here. So that's something that we need to know. Okay, so let us go to the next page. The next page is just a confirmatory presentation of what I just talked about this guy, Mr. Helium. So Mr. Helium here is being demonstrated in such a way that it makes us easier to understand that. Okay, let me just push this thing this side so that don't get disturbed, and this one that side. Okay, cool. Okay, so now it's just a confirmatory presentation of helium, means in so much that this also not helium but Mr. Neon. Mr. Neon, who had the mass number of 20, okay, and then the atomic number, relative atomic number is 10. So if you are to do the configuration of these electrons, we don't do the configuration of the protons unless you are doing nuclear chemistry. So we're gonna have 2,8. Now the 2,8 here, the last shell here is fully occupied. Okay, their chemical unreactivity is brought about by the fact that the last shells are fully occupied. So if you want to go by this kind of presentation, electron configuration, well and good. Or if you want, you can go by this by saying the first shell has got 2 electrons. Okay, these two are the ones that are presented by this one here. Let me try use a different color, black, now blue, yeah. Okay, these electrons here are the ones that are presented in here. Then after that, we have these ones, 2, 4, 6, and 8. These 8 here are the ones that are here. Now, even if we had to put another, even if we had to put another shell outside here, you find that we only had 10, and those 10, those 10 electrons are already used up. So you cannot put anything in the last shell. So because of this, this is what brings about them being chemically unreactive. And then all these elements that we talked about, they are gases at room temperature and pressure. What gases are, what elements are they? Let's just list them again. We say that the first one is helium, and then we've got neon, we've got argon, then we've got krypton, we have xenon, and we also have radon, the one my friends from Eastern can read as at random. Okay, radon. These are elements that we have. Now, you see, look at the way they are written. Not on that, even in real life, even when you're taught to write them in the just the symbol, you have to write them like that. Why? It is because of these 2 points that I'm going to talk about. One, monoatomic element, as well as the diatomic elements. Now, these are very, very important things that need to understand. Why? It's because people say chemistry is difficult, especially when we start looking at chemical equations, because if don't we understand the type of elements that we're dealing with, are they monoatomic or diatomic, you find that your chemical equation will be wrong, your balanced chemical equation will be wrong, as well as the net ionic equation will be wrong. Not on that, even when you are told to perform stoichiometrical calculations, could be the mass, could be the volume, anything attached to the chemical equation, everything falls apart in a wrong way. So that's why I've decided to bring out this point in the way that will help us. In the way that will help us. Now, what am I talking about? Okay, I've just gotten the arrow. Who does that? I thought I was getting this. Oh, yeah, something big. Good. So you see, these ones here are very, very important. Now, when you say mono, mono is a prefix that we use to denote the word one. So mono means one, and the di means two. Two di means two, like carbon dioxide, carbon one, and oxide two, CO2. Monohydrogen, one hydrogen, or dihydrogen, dihydrogen monoxide, that's water. Dihydrogen monoxide, that's water. You can also have carbon monoxide. Okay, so I'm just trying to give an emphasis on these prefixes, mono as well as di. Now, when you say these guys are monoatomic elements, what do we mean? What do we mean? Let us go back to metals. How do you write metals? Metals such as zinc, you just write Zn. Metals such as calcium, you just write Ca. Metals such as cobalt, you just write Co. Metals such as tin, you just write W from the word wanget, Latin word. Words such as copper, you just write Cu, cuprous, because these are metals. Why are we writing them like that? All metals are monoatomic elements, meaning they can exist as a single entity like that. Now, when you say they are also diatomic, okay, in the very way that we've listed these metals, that's the way you list even those are inert gases. When you're told to write helium, just write He. Argon, just write Ar. Carbon, just write C. Xenon, just write, though this one is not an inert gas. So this is what it means, monoatomic existence. Now, remember, I also talked about the diatomic existence. These guys here, we use most of these to denote gases other than the noble gases. Pay attention to that. The diatomic existence is common in gases other than the noble gases. Gases such as hydrogen. When you're writing hydrogen in a chemical equation, you just write H like this. It's very wrong. The only way hydrogen can stand alone is when it is charged, an ion. But in a chemical equation, you need to put a 2. Nitrogen also supposed to have a 2 because it's a diatomic element. Oxygen, it has to be like that. The only way oxygen can stand alone is when it's charged. And that is an ion, yet we are talking about elements. Okay, so oxygen should be written like that. So these are diatomic existing elements. They are gases, of course, they are gases, but these noble gases that we're talking about today, like Mr. Neon there, you don't put a 2. The moment you put a 2, it means you don't understand chemistry. You don't understand the meaning of monoatomic existence as well as diatomic existence. Okay, so that's what it means. And now let's go to their uses. You see, I decided to pull out some animations, rather the pictures that will help us understand these guys. So we are saying that these guys are used in inert environments. When I say inert environments, I'm talking about the environments where chemical reactions are tried by all means to be minimized. So I'll just talk about some few. The first one here is Mr. Helium. Now, Mr. Helium there, just look at the nature. If you follow the periodic table, the first element that we have is hydrogen. Forget about the diatomic existence. I'm just getting them from the periodic table. Then the other one is the second one, in fact, is Mr. Helium. Now, I want you to make comparisons, 1 here and 2. Okay, 1 here and a 4. Now, in this, the 4 doesn't look like it. In this 4 here, in this 4, we have 2 protons and we also have 2 neutrons. These are the ones that contribute to the mass number of elements. Now, these ones, then this guy here only has a proton. Okay, doesn't have a neutron. Now, you see, the proton is 1 here in hydrogen. Now, why am I saying this? These guys are very, very light. Just look at their mass numbers, they're very tiny, 4 and 1. They are very tiny. So because of that, the percentage composition of these gases in the atmosphere, the surface that is close to the Earth, the percentage of these gases is very small, if at all it's there. Why? Because they are very light. Now, how do you explain that? Look at what happens when you're burning a paper. If you have money, especially 100 kwacha, I'm sure you're going to use it to burn it, then you learn more. You have these, let's say, a bunch of papers, then you ignite them, you set fire. What happens to the smoke? The smoke, when it's not windy, the smoke does not go that way. What happens to the smoke? The smoke goes up. Why? It is because the air around here will be heated up, of course, painted with smoke, will be heated up, and then it becomes light. It goes all up. So because of this, these guys, the hydrogen and the helium, these guys are very light, so they are likely to escape from the surface. Now, why did I say that? So meaning in these weather balloons, in these balloons, the gas that you need to put inside is that gas which is light. You cannot put carbon dioxide. You just can't, because carbon dioxide is considered to be is a very heavy gas. So if you put carbon dioxide in here, you find that this weather balloon will never get to go up. But we put this helium because helium is light. So function of helium is that it is used to fuel the weather balloon. Why? Because of the mass expressed in terms of the mass and the volume expressed in terms of density. It has a low density. Therefore, it is used in weather balloons. Then the other one, as we approach the Christmas at night, you can just hear the sound. You turn around and look at where the sun is coming from. You see the flashing of light from the advertising bulbs. Now, inside of the advertising bulbs, the gas that they put is neon. Why neon? Because neon has the capacity to glow. It glows into a red hot when electric current passes through it. Yeah, so we use neon in filling the advertising bulbs, because when the electric current passes through it, it glows into a red hot. Okay, we got the last one. The next day, I think this is the last one that I'm going to look at. It's called Egon. Egon here is not Argon. People from each part. It's called Argon. Now, this Egon here is also used in the bulbs, but these bulbs are not the ones for advertisement. Just these ordinary bulbs. Yeah, you can have a bulb here, and then here we have the filament. Okay, then you have the soldered contacts here, and then you have this thing here. Now, inside of these bulbs, we put argon. Why? Because argon is there to create, of course, this thing here. If you were to remove, if you were to create a vacuum space here, you remove every gas, this bulb will polycar. So the only way it cannot polycar, to prevent the polymerization, is by putting the gas. Now that gas we're going to put in there is the one that creates an inert atmosphere to prevent the blowing, to prevent the reaction of the filaments here. Now, the moment you have an opening where the wind is entering or where the air is entering from, the moment the air goes in there, I know that air is a mixture of gases, and among them, there's this guy, oxygen. And when oxygen goes and comes in contact with a heated filament of wanget, a tungsten, you find that the filament will cut. And the moment the filament cuts, you're going to say the bulb as polymerization, the bulb is blown. So to prevent that, you make sure that you put a gas that's going to create an inert atmosphere. Okay, so we have 2 more pages. Let's now look at the transition element. So we are done with the group O elements. Yeah, last one but not the least, let's look at transition elements. What elements are they? You see, these elements are the ones that are here. Look at, there's a very big jump from 2 to 3. okay, from 2 to 3, there are these ones that we have left here. All going all the way up to that. There's even a zigzag kind of a line. So these are the ones that we're talking about. Of course, together with these, the lanthanides and the leuthanides, yeah, the lanthanides and the actinides. Now, these guys here are supposed to be fused. That's what it's supposed to be. From the lanthanide to cerium, this follows. And then after ruthenium, you go to this guy here. And then after the actinides, you go to that. And then this guy is the last one. Now, we're talking about these elements here. Now, this is what we call the D block or the central block. But why are we calling it the D block? Mostly we call them the D block from the pure chemistry point of view. Why? Because when we're writing the configuration, we don't just write 2, 2, 8, whatever kind of things. We follow the orbitals, and these orbitals are given the letters. There's S, there is P, there is D, and there is F. Yeah. And of course, you say this one can only take the maximum of 2 electrons, this one 6, this one I think 10, and then this other one takes about 14. This is from pure chemistry. Yeah, but I was just trying to say, I was just trying to give an emphasis why they are called by the D, letter D, is because of this the orbital, the D orbital. So we're talking about these elements that are here. Okay, so let's go back to the page where we are. Where are we? We right over here. So these transition elements, what we can say about them is that, so these transition elements, what we can say about them is that they are found in the center block of the periodic table. You saw what happens to, between period 2, between group 2 and group 3. We had them, okay. So these are these ones. Now, quite a lot. We can just maybe look at the examples. We've got cuprous, copper, Zn, zinc, silver, Ag, mercury, Hg, gold, Au, okay, lanthanide, La, actinide, Ac, thorium, Th, bismuth, Bi. They're quite a lot, quite a lot, quite a lot. All these are the ones calling transition elements. Now, why do we call them by that name? Or what physical properties can we pull up here? So the physical property is that these are the ones that I've listed. Of course, I'm going to talk about some more. One, what we know is that they are called transition elements or transition metals. So they are all metals. That's the first one. All of them are metals. First physical property is that they are all metals. All of them are metals. Yeah. And because they are metals, most of them we expect them to be solids. Okay, so a metal has to be a solid. Can you find a metal which is a gas? Of course not. Yeah. So at room temperature and pressure, that is. But now there's this stubborn metal, a transition metal, Hg, mercury. This guy is a liquid. So there are times they ask a question to say, mention one transition element which is a liquid at room temperature and pressure. It's mercury. Yeah, and yeah, that's one thing I need to know. So we're saying that, yeah, it's even here. It's been confirmed. I thought I didn't include it. Yeah, so we're saying that because they are metals, they have high density, they have high melting point as well as boiling points. They are good conductors of heat and electricity. Now, there are times when they ask Elena to state the use. Okay, there are times when they ask Elena to state the use of the element and then with respect to its property. So we're gonna come back to these properties. Then there are ones that we are saying they are solids and at room temperature and pressure, except for mercury, which is a liquid. And then the other one is that they're ductile. Now, when you use the word ductile, ductility of a metal is the property that tells us that when you have a beam, when you have a bar or a rod of a metal, you've heard of metal cycling. These are metals, the rod, this bar of a metal, you can recycle it and then put small wires Copper wires are very tiny, but what they get from the mining refinery plant, they get something big, but they are able to draw them into wires. Why? Because of ductility. The other one is malleable. Malleability is a physical property of metals that helps us to tell us that these metals can be drawn into small sheets. We've seen of iron sheets, yeah, but you can also have a very big rod of iron, but we can also get them to small sheets. Now, another one, the sonorous. These metals are also sonorous. Let me just put up the word here, sonorous. Let me write it here, sonorous, sonorous. It sounds as if this element is an element that has in total. No, sonorous, we're talking about the property that describes or that talks about them being able to produce sound, have the ability to produce sound. So what happens if you have a metal bar, then this metal bar has got maybe these ends, okay? Then this part is fixed. When this part is fixed, then you hit, you menya. To menya is to chayambama, you beat, you hit, not hitting of changing temperature, but you hit with maybe plastic or anything. You find that this will start vibrating in a to and fro arrangement, up and down, yeah, and by so doing they produce sound. So the property of metals that describe the fact that they're able to produce sound when they are hit, that's the word we use, sonorous. So that's another physical property. Now these are physical properties, of course, some more. With the other one, you can say that they are colored. Of course, quite a lot I can pour out. But let's go to their chemical properties. The chemical properties, these are the properties that you can tell after carrying out a chemical reaction. So what property can you pull out? What chemical property can you pull out? Okay, so one, they use as catalyst. This is talked about in the previous slide, but in the next slide, but I'll just talk about here so that we forget about the next one. So the other, what we're saying is that they are used as catalysts. Catalysts, we say these are substances that change the rate of a chemical reaction, either speeding up or slowing down. So where do we use them? The first one is ferrous. Fe, ferrous, fine iron, is used as a catalyst in the process we call Haber process. Haber process is a process where we produce ammonia by the reaction of nitrogen and hydrogen, and then at the end of the day, ammonia is produced. So in that process, we'll produce ammonia. The process we call it Haber process, and the catalyst that we use is fine iron. Then we also have this guy, PD, palladium. PD or PT. PD is palladium, PT is platinum. Where do we use them? When you start looking at organic chemistry, they are what we call alkanes. Yeah, let me just type here. Yeah, so they are what we call alkanes. Alkanes and no, not alkanes. Alkanes, these unsaturated compounds. For you to produce the alkanes, you need to react them with hydrogen. Hydrogen. When you react them, what you produce is an alkane. Not lacane, alkane. And this this reaction is called hydrogenation. Hydrogenation. So hydrogenation is a reaction where alkenes are reacted with hydrogen to produce alkanes. We can understand this from organic chemistry. Now, for this reaction to happen, you need to have a catalyst. And the catalyst that we use, you can use either palladium or platinum. Yeah. And how that happens, is it going to produce geometrical isomerism and all that, geometrical and all that, the cis, the trans, May not talk about this later, or may not talk about even them later, maybe for advanced chemistry. So what we're saying is that pure iron is used in the Haber process, and then palladium or platinum is used in the halogenation of alkanes. So that's just a complementary test that these ones are used as catalysts. Okay, then the other one is that they have many they have many valences. Yeah, I'm also going to combine these two here. I'm going to combine them. Remember, I also said that these elements are colored. Yeah, most of them are colored except for zinc. It's because the D block is fully occupied. Yeah, because of the D block. Yeah, so the number of electrons in the D shell, and you can understand that from a pure chemist, unfortunately, the number of electrons in the D shell will determine its color. If the D shell is fully occupied like zinc, zinc is white, it's not colored. Oh, white, it's not colored. Rather, it has to have a different color other than white. So so these guys have variable valences. They have more than one, except for zinc. This one does not favor zinc. Zinc has the valence of 2 only. So at times they ask name a transition element that has a fixed number of valences. Please do not hesitate to go for Zn, which is zinc. So yeah, I was saying they've got variable valences, and then those valences, each valence has its own color. So I'm going to combine the two. Copper here. Copper 2 is blue. Copper 1 is not blue, has its own color. So copper's got two valences, copper 1, copper 2. What about iron? Iron also has these ones that we can talk about. Iron 2, which is pale green, then iron 3, which is reddish brown. You get to have a nail, you pour water on it, or just leave it outside. Then when it comes in contact with water and oxygen, you find that it turns brown. So that brownish you find around the nail is because of the oxidation of this iron. This iron from Fe to Fe3 plus, then plus 3 electrons. So this is the oxidation of the ferrous. Now that brown color you see, it's because of the presence of these guys. Yeah, so that's one thing that we know. Then from that, we say they are used as reducing agents. I may not talk about this because they're saying because they lose electrons, but the losing of electrons may not be the full completion of the explanation of reducing agents. But anyway, you can even see that this ferrous, which was here, has lost 3 electrons and then it has been oxidized. That's why it's a reducing agent. Okay, so let's go to the next one. The uses, of course. Yeah, now this, okay, this is the last part. Okay. Remember, I was saying that these guys, at times the examiners will ask you to give the use of an element supported by the property. So look at this guy here. This guy says they are used in the, they are used in making cables. So there are 2 things here. Why? What things are here? One, there is a use. They are used in making cables. They are used in making cables, and then they have also added the property that supports that. Okay, so we are saying they are used in making cables. The property which supports that is that they are good conductors of electricity. They are also used in making kitchen utensils. You cannot make a pot out of the wood. It can burn, not only that, yeah, it can burn, of course. So why are we saying that they are used in making pots, pans, forks, spoons, and all that? Because they are good conductor of electricity. Then the other one was The one which is up, where we're saying that they are used as reducing agents, the property is because they lose electrons. Okay, now let's look at the last part of today's presentation. The last part of today's presentation, which is the other uses. We are saying they are used in making alloys. They are used in making alloys. Now, these alloys, they are quite a lot. One, but by the way, let me talk about the alloy. An alloy is a compound that is made up of two or more compounds. Sorry, an alloy is a compound that's made up of two or more elements that are physically combined. So there are quite a lot of alloys. The first one is brass. Now, it's always important to understand the elemental composition. So brass is made up of zinc and copper. We have Zn. In the molten state, you mix with cuprous, then you have brass. The other one is bronze, as if it is coming from Monze, where my friend is. Bronze is a combination of copper and tin. Now, this time around, it's copper and tin. Wanget. Okay, the other use is that they are used as catalysts. Of course, these ones I've explained, so no need to worry about. But except only the here, I was supposed to highlight here only the examples. Oh, sorry, on the examples. The alloys. I have to talk about steel, not steel Yakub. Stealing money from people. No. Remember, there's E here, double E. So steel is also an alloy. Now there are quite a lot of types of steels. There's stainless steel, there's milled steel. So even as you get to watch this video, please research on steel, the types of steel and the elements present. When you say tangless steel, it's carbon and copper and what? Is it just carbon and copper? Then you say milled steel. We've got high carbon steel, low carbon steel, and all that. I'm challenging you to look at that and understand what is involved. So at the end of this video, when you're done watching a video, I want you to give an attempt to this assessment. 5 times. Watch the video, understand it, do the work. When the work is done, please send the solutions to my WhatsApp number. And my number is plus 26097 5578694. So you gotta send the work pictures, or could be something typed, to that WhatsApp number, then I'll be able to review it. All right, so thank you so much for your time. I appreciate it.